Um, Hello. Thanks for coming to this presentation. We're going to talk about some interesting stuff regarding TLS. And we'll also have not one, but two cool demos at the end, so brace yourselves. First, allow me to introduce myself. I work at Bitdefender. I do all sorts of crazy low-level stuff and ransomware-related cryptography research occasionally. And I also like to play CTFs. I'm with my boys playing the CTF right now. If you have a chance, try some CTFs yourself. It's really educational. All right. So first of all, I would like to tell you what this presentation is about and what it isn't about, so you know from the start. It isn't about faults in TLS per se or in the underlying implementation in various crypto stacks. Neither is it about attacks on the cryptographic level, bit flipping attacks, Bleichen-Bacher padding work or something like that. No. Well then, you may ask, what is it about? Think of it as an experiment. We decided to model a very powerful adversary. We call this hypervisor in the middle attack. And so imagine it in the context of cloud providers, right? So in the cloud, the provider can see stuff from the VMs. They can see HTTP traffic. But can they also see HTTPS traffic? Well, not really, because it's encrypted, right? And we wanted to see how far they would have to go, how intrusive do they have to be to decrypt your HTTPS traffic as well. And in so doing, we got some really unexpected results that you're going to like. But why did we start this? How did this idea come about? We're operating a honeypot farm. You know what honeypots are, right? They're just VMs spread all around the globe, and attackers can gain access using weak credentials. And what we want to do is study what a hacker looks like, how he thinks, and what exactly are the latest trends in hacker mischief. So we set these root credentials very weak. But then how are we going to see what happens behind the scenes on that VM? Because lots of attackers just try and see if anything is modified in the VM. So we wanted to see what traffic they do. HTTP is okay. HTTP you can see from the hypervisor. But HTTPS is used nowadays. Why? Because all hackers have access to let's encrypt, right? The second use case is malvertising. So it's a bit opposite. You want to script some browsers and make them scour the internet through all the shady corners in the hopes that you get infected. This is exactly the opposite of what a normal user would do. But that's not our target. Our target is to obtain samples. However, most of the times, these infection samples come in stages, and when the first stage is downloaded, it's usually fed through some TLS-enabled site, either the advertisement sites or the attacker's servers. And this first stage will set everything up, but before it actually downloads the next stages, it checks that if there's something wrong with the machine, if it's under scrutiny. All right. So let's see what are the current solutions for getting TLS traffic, and then we'll see why they aren't enough. So the first solution is called SSL keylog file. It's just like a regular keylogger, but instead of logging keyboard keys, it logs SSL keys. And actually, it's implemented in Firefox and in Google Chrome by default. You can just point the environment variable to a text file, and it dumps output like this. Hex mumbo jumbo, it doesn't make sense to you, but if you feed it into Wireshark, it transforms traffic that is captured like this into this, which is human readable, almost, hacker readable, let's say. HTTP response 200 OK. All right, so why don't we use this? Well, as I said, it's only implemented in Firefox and Chrome. And for example, in malvertising, we're also interested in exploit kits, in Silverlight, in Flash, whatever. We want to see Internet Explorer exploited as well. So we don't have this option in Internet Explorer. And moreover, it's really visible. I mean, it's an environment variable. Another solution, speed quiz. Do you think this connection is secure? Looks like it, right? It has the green padlock, secure connection. Well, now do you think it's secure? Verified by Superfish. This is a root CA. It's a typical solution used by legit businesses, by security proxies such as the Excel and Burp Suite, and by shady hardware vendors such as, you know, who issued Superfish. And because you have to add this to the system somehow, it's visible by malware, right? But it's visible by it when it escapes the browser. However, a recent paper a few years ago showed that you actually don't need to escape the browser. It's a really cool research. All right, so now let's say that we don't want to modify the VM at all. Let's do something more rocket science. What are the current solutions for this? There's a framework called Panda, which is excellent. I suggest you look into it. And what they do is, instead of running the machine virtualized, they emulate it at a cost, and then they instrument each and every instruction. They set some trace points, some tap points, whenever the keys are calculated. And having these trace points means that when you figure out that you're at that point of execution, you can just stop the machine for a while and get the memory, the keys from the memory, then and there. But as the author says himself, it transforms 12 seconds into 2 hours. It's a huge overhead, and moreover, we assume that the hacker can do, the hacker or the honeypot compromiser can do whatever in that VM. So maybe they upgrade the crypto libraries, maybe they do something else. This means that you have to reanalyze the VM and you have to modify the trace points. So it's non-portable. You cannot get the keys from the memory anymore. But about that memory, this is a key idea. Think about it for a bit. You have a TLS connection. It's still active. So this means that the keys must still be in memory. Why is this? Well, if the connection is still active, then you're supposed to be able to both receive packets and send them. But if you're going to receive packets, you have to decrypt them, right? And if you send packets, you have to be able to encapsulate them through an encryption layer. So this means that if a connection is still active, the keys are in memory. So we're in the hypervisor. That's our adversarial model, hypervisor in the middle. Why can't we just access the memory and get the keys from there? Well, it's not so simple. Maybe it's Linux, maybe it's Windows, maybe it's S-channel, maybe it's OpenSSL, boring SSL, libNSS. Multiply these together, and ultimately, you just have to dump the whole memory. So it's a real problem. You don't know the location, you just dump all memory. But when you do this, say you have a VM with 4 gigabytes of memory, it will take a lot of time. It will really be noticeable. In the context of cloud providers, you don't want to violate the SLA. So it's a problem. Moreover, as you will see in a browsing session, the browser doesn't just do one connection. When you connect to google.com, it doesn't just gets one page. It also gets the advertisements, the static content, the dynamic content, referrals, whatever. So if you do this at each and every connection, the disk space on the hypervisor will quickly fill up. But for the moment, we're engineers, right? Let's simplify the problem for a bit. We're going to decrypt just one connection. For this, we're going to accept for the moment the penalty of dumping the memory to disk. And decrypting just one connection. So we have the memory dump. What are we going to do with it? We can apply volatility on it, and it will take a lot of time. We want to do it in real time, right? How are we going to distinguish correct keys from that memory dump from garbage? Well, these are our problems. We solve them, each and every one of them, quite elegantly, actually. But to actually see what we did, we will have to dig a bit deeper into the TLS handshake. All right? So I'm going to present an overly simplified version of the TLS handshake, but for all intents and purposes, you can consider it as factually correct. So how does the TLS handshake work? The server is listening to requests, right? And the client does just that. He issues a request, but before doing this, he has to negotiate a secure channel with the server. All right, enter the TLS handshake. He will send a client hello, as it's called, which contains the version of TLS that the client supports, a list of tuples called the cipher suite list, which contains asymmetric crypto for key establishment, symmetric crypto that will be used throughout the lifetime of the connection, and authentication code. And there's also an interesting value called the client random. We'll go over this in a bit. To this, the server responds with a certificate so that the client knows he's talking to who he thinks he's talking to, a cipher chosen among the list that the client supports, and the corresponding server random value. All right. What happens now at the dotted line? Well, under the hood, there's some math. I'm not going to go into it because actually we don't need much of it. But what each party does is they compute, using the information they have, a context, a symmetric encryption context. These keys that are computed independently by both parties, they'll be the same keys, have to match. So when they do this, after they finish, the client will send the last packet of the handshake, which is encrypted. The server, the same. He will send the first encrypted packet. Only after this has happened that the actual application data has been sent, can be sent. So only at this point can the client send the first byte of the request. So what does this mean? Well, we need some more info on the server random and the client random. The standard says that you need both values to be able to compute the keys, right? So we said that both parties will compute the keys on their own, but they need information from the other party. Because of this, it means that at some point in time, you cannot have possibly computed the keys, right? Because you haven't received the information from the other side. And let's see this from the client's perspective. Immediately before the server hello has been received, the keys cannot have been generated because the client only has the client random. He doesn't have the server random, nor does he have the cipher suite. And when the client finish has been sent, the first encrypted packet, it means that the keys must still be in memory. Why? As we said before, the application data has yet to be sent, so the connection is active. All right, this means that we don't need to dump all the memory. If we are able to track memory between these two events, and it's a big if we are able to somehow get some signals from the network that, look, now start getting the memory that is being modified and now stop and dump it, we could conceivably get only a small portion of the memory, and that will be all we need. This will lead to a dramatic decrease in what we need to dump to the hypervisor. But can we do this in real time? Can you actually track pages which are modified? Well, yes, you can. Think about virtual machine live migration. So you have a machine in a data center in London and in a data center in Amsterdam, and you want to move it because of, I don't know, it's better speed, better bandwidth, whatever. What you do is the following. We will consider the Zen hypervisor. It has a mechanism called log dirty, which is exactly what we need. It logs dirty pages, dirty/modified pages. What you do is you issue this mechanism, and all the memory gets flushed on the network to the Amsterdam data center. Okay, but the first machine is still active, right? It's live migration. So when this transfer finishes, the machine in Amsterdam will have an inconsistent view of the physical memory of the machine in London. So you need to do this iteration again, only with the pages that have been modified. And this log dirty mechanism helps you just with that. At first you send 4 gigabytes, as we said, but at the next iteration, to have a consistent state, you only need to send, let's say, 100 megabytes. And in the next iteration, 50 megabytes, 10 megabytes. This inconsistency will drop and drop until you reach a certain threshold. So then you just stop the VM and start it in Amsterdam. This is how it works, and if you think about it for a bit, this is exactly what we need. Between 2 timestamps, you can track the memory that has been modified. All right, but is this only for Zen? Well, no. Most modern hypervisors support this in some way, either through write protecting pages, write protecting whole page tables, or something really curious. Recently, there's even a processor extension from Intel called page modification logging, which does just what we need. It's really convenient for TLS decryption somehow. Okay, so let's do a brief recap. So you live in the hypervisor, right? You have access to the traffic, and what you're going to do is set some dumb IP tables rules. Why? Because the TLS handshake is plain text. Well, not plain text, let's call it plain hex. It's dissectable by Wireshark. So when you see that a server hello is coming from outside and it's about to enter the guest VM, you stop it in transit, you start this log dirty mechanism, and then you let the packet go through. Correspondingly, when you see that the packet is exiting the VM and it's about to go on the network, you stop the you stop the packet, you issue the log dirty mechanism to get the pages that have been modified, you still keep the packet in transit for a bit so that you don't stop the VM, and you dump all the memory pages on the hypervisor that have been modified. And then you just let the packet continue its course. And this is only this you have to do at a TLS connection. The result will be a micro memory dump, as we call it, really small, not 4 gigabytes, as you'll see, but this can be processed offline anytime. So you have the traffic from the hypervisor, and if you combine it with this, you get the keys. We'll see how. But the important thing here is that you can do this either 1 minute after the connection has started, 1 month, 1 year, whenever you want. So you can have history. Right. Some numbers. On a Linux VM, the memory dumps are about a couple of megabytes for a connection, which is a bit different from 4 gigabytes, right? On a Windows, because of bloat, and for bloat I mean graphics interface, of course, you have a couple of tens of megabytes memory dump. But what we're most interested in is if it's noticeable. If the hypervisor does this to a VM, if it's noticeable. And through some tricks that you can see in the paper, we managed to get it down to 0.5 milliseconds tops, but usually it's 0.05 milliseconds. And this is on a hardware that doesn't even have page modification logging. And the actual page dump time is a couple of milliseconds, and as we said, this is included in when you keep the packet in transit. So you don't even need to pause the VM. You pause it only when you issue or reset the log dirty mechanism. All right, revisiting our problems, we don't have to dump 4 gigabytes anymore. We still have multiple connections, but space won't fill up as quickly, right? But there's still the second problem. So we have the micro memory dump. What are we going to do with it? We have to process it somehow. And this is what we're going to do next. Apparently, you have the key format. You have various parameters for the cipher suite. Assuming, so let's simplify the problem a bit again. We're going to assume that the encryption keys are in memory. So we're going to try all substrings. For example, AES-256, we're going to try all 32-byte consecutive strings. How are we going to know when we arrived at the correct key? We have the traffic from the network. We're going to try and decrypt it using the cipher suite, but we don't know what's behind the decryption. What are we going to do? We're going to revisit the TLS handshake again. We said that just before the TLS handshake finishes, we're going to use, just before the handshake finishes, you have 2 more packets encrypted, sent from each side. The client finished is encrypted, but it has a fixed form. It starts with 14000C. So if you just try all the keys, and somehow you get to one that starts with this, you have 2 possibilities, right? Either you've stumbled upon the correct keys, or you have a false positive. All right, let's see the false positive rate. It's 1/2 So this is 4 gigabytes. So you need a 4 gigabyte memory dump to get just 1 false positive. But we don't have 4 gigabytes. We have 4 megabytes, so let's say 40 megabytes for Windows. So it's cool. But this only works if you can actually decrypt those first 4 bytes. It works for stream ciphers, but for CBC and GCM, not so. So let's see what exactly, what are the cipher suites that get selected, right? We said the server selects the ciphers. Unfortunately, only 5% is prone to our technique, only stream ciphers. So 20% CBC and the rest GCM. All right, let's tackle the next one, CBC. As its name implies, it just chains blocks together. So when you want to decrypt the 3rd block, you need the 2nd block. When you want to decrypt the 2nd block, you need the 1st one. All right, but we need to decrypt the 1st one. For the 1st one, you have to use the initialization vector, which is also part of the key material as the key, so it's somewhere else in memory. So you will need to brute force that as well. You have one brute force for the IV and another one nested for the key. So you have quadratic complexity here, which isn't actually real time. But there's another thing. This is a block cipher, right? When you encrypt 6 bytes, the encryption goes to 16 bytes. So you need padding. So we don't have access to the decryption of the 1st block, but we have access to the decryption of the last block, which is predictable padding. And it's the same as before. You just don't use the 1st, you use the last block and get the padding. All right, CBC down. Now let's tackle GCM. Well, it looks a bit difficult, right? But we're going to split it into 2 easily digestible parts. GCM counter mode. Half of it is counter mode, half of it is authentication. So you just have a counter that infinitely increases. You encrypt this counter, and you will get a pseudo-random stream, an infinite pseudo-random stream. And you use it just like a normal stream cipher. You don't have the padding, unfortunately. you encrypt it, and at the end, instead of using MD5, SHA-1, SHA-384, you use the GCM. You combine the ciphertext blocks, you do some finite field math magic, and you end up with a tag. This process is really fast. That's why it's combined together. All right. So why can't we have the same approach as before? Think about it. You have two directions possible for the brute force. Either you use the counter to try all encryptions and see if solved with the ciphertext you get a plaintext starting with 14.0c, or the other direction around when you decrypt. But if you want to decrypt, you only know half of the plaintext. So you will have quadratic complexity again. And the counter is actually half random from the key material, half predictable. So quadratic complexity again. All right. How do we solve this? Well, using the tagging part in the algorithm, I don't actually have time to explain, but you can see in the paper. In short, what we do is just reverse some flows in the tagging. Instead of using the ciphertext, the authentication data, and the encrypted counter to get a tag, we will use the ciphertext, the authentication data, and the tag to get an encrypted version of the counter. With this encrypted version, we try all the keys, and if it matches this predictable value, we're all set. So this time it's a plaintext attack on the counter. All right. Some numbers again. If you have a memory dump that is completely random, which isn't usual in practice, and you try getting the GCM keys, it will end up about 7 seconds. If you throw more hardware at it, more CPUs, you will get a really cool speed up. Here we only have 6 CPUs, but 12 times speed up. You can read about it in the paper if you're really curious. And another thing is that when you do a micro memory dump, or any memory dump, it's not completely random data. It has structured and low entropy data. It has lots of paddings, lots of text. The keys from the key material have some good statistical properties. So you can add these heuristics and you will get really a bigger speedup to about a couple of hundreds of milliseconds. But think about it. As we said, a typical memory dump is a couple of tens of megabytes, right? So this means that it's actually a couple of tens of milliseconds on each micro memory dump to process. So we can actually consume the memory dumps as fast as we can produce them. So space won't fill up at all. All right. So that being said, I can go on to the demo. We have 2 demos. The first will show you the actual internals of the TeLeScope. Okay. So the setup is the following. I have a laptop running Zen, and I have a machine that is running Windows 10 as a guest VM. All right. Our guest VM, where exactly is it? It's this one. Do we have connectivity? We have. Okay. So I'm going to start the TeLeScope and attach to that VM. Sorry. First, let me start up Wireshark. We want the traffic capture, right? And we attach to the VM. We have to specify the IP that has been assigned to the VM and the name. Okay, it starts logging. Wireshark seems to be working. Okay. Yeah. So what we do is a regular browsing session. We go to Google, Mail, and sign in. But hang on a bit. Before we start typing our credentials, let's check that it's a secure connection. Is it a secure connection? Yeah, it might be. But we have to check. Otherwise, it will be superfish again. All right. GeoTrust, Google, authority, accounts, google.com. All right. Seems legit because it is. Connection encrypted with Diffie-Hellman, RSA, GCM. All right. Seems good. Don't stay signed in. Okay. Yeah. So you're going to see my password, so I decided to add two-factor authentication. Okay. Three, 5, 8. Yep. And with the demo gods willing, all right, we logged in with our top secret docs here. Gonna stop Wireshark and save the capture just to be safe, to be on the safe side. Okay. So what we have here, almost unseeable. This is worse. So we have a lot of sessions, right, for each connection. So our browsing session only lasted for a couple of seconds, but you see here a lot of connections, right? As I said, because of static traffic, static content, advertisements, whatever. Okay. How big are they? 200 megs. And there are about 30 connections, I think. So let's process them. I have a quick script that just iterates over the directories and processes them. Boom, done. Let's try it again. And see how much time it takes. 1.5 seconds for 30 memory dumps. All right. We have the Wireshark traffic. I'm going to filter just on the hello, so you see all the connections here. All right. So actually, if you just look in Wireshark and you don't plug in any keys, what do you see? You can only see the site that is being requested on the right-hand side. Well, without zooming, you cannot see anything. We're going to look at this one, accounts.google.com. I have a feeling this will be the one we're interested in. If you do TCP stream, this is what's on the wire. You have the request, you have the certificate, and everything else is encrypted. It looks like garbage because it's encrypted. If you use Wireshark's feature for follow SSL stream, it would use some keys, but it doesn't have any SSL keys so far. Okay, so now session keys. All right. Yeah, we have the keys in there. So I'm going to do a bit of a hack because of Wireshark. Boom. Did you see that? Something changed. Why? What exactly? Instead of SSL, you now have HTTP. If we do the same follow SSL stream, what do we get? Does this look plain text to you? It's still garbage? Well, no, actually, it's HTTP 2.0, which is the latest rage in browser technology. But, whoa, we have something here. Email, hack in the box, TeLeScope proof of concept. Done, decrypted. Do we also have the password? Lame password 42. So now you can log in into my account. But actually you can log in, right? Because you don't have my two-factor authentication key. Yeah, it's around here someplace. Anyway, you can just get my cookie, so you're all set. Okay, so now what we have is TCP on top of SSL on top of HTTP2. So everything is decrypted. You have this capture file, and you have the keys. You're all set. You can decrypt this at any moment in time. And did you actually see any overhead? Did you see any slowdown? No. This can be done by the cloud provider whenever they want. All right. So I can close this. And the capture. And this one. And OK. But so let me show you something else. When we did this, let's see how much time was the machine actually paused. So update the timestamp of dirty pages. So paused VM, 0.043 milliseconds. 0.048 milliseconds, as we said. And the page dump time, a couple of milliseconds. So it's really unnoticeable and pretty scary, actually. All right. Now, I said I have another demo. This one is to put everything in context, right? So what I showed you before, it's just command line stuff. You have to do it by hand. But as I said, we have some honeypots. And we want to see what the hackers look like, what the hackers do on our machines. So we integrated the TeLeScope along with another instrumentation framework that we have, and we're going to see what we see. But we need a hacker, so we want to see what a hacker looks like. Do you know the stereotypical portrait version of a hacker? If you find it, if you search for it on Google, apparently there's some sort of pattern. You cannot be a hacker without a hoodie. So I'm going to transform into a hacker. And let's do this. All right. So I've compromised the honeypot. Wow. What am I going to do next? Date. It's the date of today, apparently. Who am I? The webmaster. All right. Seems legit. I'm going to download my files from a server that I control. But no, let's test another thing. Conference.hackinthebox.org. It's HTTPS. I'm not sure if you can see it. I'm going to zoom in for a bit. This is my command. Yeah. Index HTML. OK. Now, let me do another one. This is a site we control for various reasons. Proof of concept, all right. And I'm going to download some samples. The first of them will be dropped on the file system. So what it is, it's an ELF binary, right? The second one, I'm going to try something else. I'm not going to even touch the file system. I'm still going to download it from HTTPS, but I'm going to connected directly to bash. All right. Wow, owning the system. That sounds unfortunate. You have been owned. Wow. Okay, so I compromised the machine. I can get out. Cool. So hacker mode off. Let's see what we see from the hypervisor. So you can picture us as the cloud provider for hackers. Whoa, whoa, whoa. All right. So let me explain what you're going to see here. We have two instrumentation frameworks. One is TeLeScope, and another one is called Finesse, which just logs syscalls, but it does so from outside the VM. We mentioned it briefly in the paper. And what we do is, using these frameworks, we instrument and we get events. Events go to a data center, and then they are correlated, and we can use them to synthetically replay what hackers did. So on the left, you will see the actual events, and on the right, you will see the pseudo-terminal events, which are as well captured from syscalls. Everything is synthetic. So I logged in. Slow typing skills. Yeah. Conference hackinthebox.org. It's HTTPS. So from the hypervisor, I'm not supposed to be able to see this. Whoa. We have an event from TeLeScope, and it says that an HTML document has been received. Okay, so I'm just gonna pause the replay for a bit, and let's check this out. Let's save it to samples, and in samples, boom, HTML, Hack in the Box security conference. So this was HTTPS. All right, let's carry on. We're mostly interested in the actual samples, right? That's what the honeypots are actually for. Whoa, this one is red. I wonder why. Because VirusTotal flagged it as with detection ratio of 39 out of 56. Engines detected it as virus. So let me reiterate this. Sorry, it's HTTPS, right? So from the hypervisor, you're only supposed to see TCP, but with the TeLeScope incorporated, you can see this, and well, it's real time. Okay, and the second one, the sample 2. It never touched the file system, so what did it actually do? You have been owned. I don't think so. 857, this is the script that got transferred from 443 HTTPS. What's hash 857? Boom. Owning the system, just slept for a bit. It's a bit lazy. You have been owned, but not really. We're the good guys, right? Yep. So this is how it looks like. This one was the virus. Yeah. So that's how it looks like from our dashboard. This concludes my second demo. And the thing is, this isn't actually limited to TLS. Because it piggybacks on top of asymmetric crypto, it works with anything that negotiates keys in some formal manner. You can use this with VPN, you can use this with SSH, and even Tor, as long as it's in the guest VM and you have access to the hypervisor. Which is pretty neat, right? It makes you think whether this has happened to you or not. If it has happened, you probably haven't noticed. it. And if it's happening now, maybe, I don't know. I'm not sure whether you're going to be able to notice 0.01 milliseconds or not. In conclusion, you saw the proof of concept, you saw how it works, you saw how it can be integrated in something bigger, and the key takeaway here is that if you're not in complete control of your bare metal, then all bets are off, basically. It's pretty scary. Questions, please.
Any questions?
Yeah, please.
So I guess you have also built the same thing for actual servers, like decrypting client connections. Cool. Maybe another one. Have you built all these VPN, Tor?
No, not yet, no.
Is it planned for the open source project?
Yes. We still have some things to do with TLS, but after that we're going to probably go to SSH, and then...
Okay, cool talk, thanks.
Yeah, thank you too.
In the back?
Well, in order for this to work, you need to have an hypervisor or a mechanism that allows you to log dirty pages. Have you tried this within an operating system, so without any hypervisor? And how is the response? Of course, you have
Can you be a bit louder?
Yep. I will try again. So the basic technique requires an hypervisor for you to log dirty pages. Have you tried these techniques within an OS, such as using the page handling and other techniques, and how fast is that? Okay, so you're thinking of a setup that doesn't involve virtualization at all? Exactly. It can work, of course, but if you're already in the OS, why don't you just get the keys from there? No, definitely yes. I mean, I was interested in the speed of the technique, basically. If you do it from the OS, it will certainly be slower. Okay, well, thank you. Yeah, thank you too.
Your technique assumes the key is in memory. If the key would be obfuscated or scattered around in memory, it would be much more difficult to find it, because you would have to try all sorts of permutations or XORs or whatever. You would need some extra information from the OS. You would need to see if it's a certain library, how it obfuscates, if it does that. But ultimately, it would just remove the real-time factor from our approach. It's still polynomial. Right. Okay.
Any more questions? I have one actually. For the CBC mode, you're using the padding detection. Does that always work?
Yeah, it pretty much works, yeah.
Because if the packet aligns at the right border, then there's no padding.
No. If it aligns, then you have a block with just padding.
Ah, okay. Very good.
Yeah.
All right, if there are no more questions, then I thank the speaker, and the demo gods have been with you.
Yes, thank you. Thanks.